right, and now our second epic talk of the day. Simon Peyton Jones will tell us about type inference using constraints.
Okay, great, thank you very much. Yes, good. Okay, so same rubric as before. Please make comments and ask questions as we go, and we'll have a lot of fun together. We will finish in exactly 30 minutes' time, regardless, somehow. Okay, so here is the plan for a fairly conventional, type inference or algorithm. What happens is you have some source program, and you write some more or less difficult type inference algorithm again, and it rejects the program with some error messages if it's bad, and otherwise it accepts the program, in which case it produces, no output at all. It just says good program. Okay. So, I want to keep it this is an implementation workshop, so I'm going to put up type signatures as we go. This is what a type checking function might look like. It takes an expression, and we talked about this morning, the expected type that it has, right? And in some monad, it produces no result. That's the unit at the end. But what does the monad do? Well, it does at least three things. It's got to keep the type environment, which keeps track of what variables are in scope and what their polytypes are. That's the gamma part in our types thing. That's a kind of reader monad kind of thing. It's got to be a place to emit error messages. That's a kind of writer monad style thing. And then it also has to deal with unification, which you might think of as being a sort of state monad, but it's growing a substitution from unification variables to types. Or if you're going to do it imperatively, it's actually done a side effect on a mutable variable, which of course is what we really do. But if you're thinking more kosherly, it's just a substitution that you're building up as you go. Okay, so that's the monad. We're going to have an ambient monad all the time. Right, now, so the second thing we're going to do as we go is we're going to elaborate the program. What does that mean? That the type checker, as well as rejecting the program if it's bad, will also produce a new elaborated program as its result. So what does the elaborated program do? It makes explicit the type instantiations and applications that go on. So GHC is a little unusual here. In GHC, we take a Haskell program, we produce an elaborated program, which then gets converted into system F, which is statically typable, right? So right the way through the compiler, from the front end right through to the back, we got a statically type checkable program in system F. That means that we need to know where the big lambdas are and where the type applications are. So here's an example. I've got foo here, which calls sort of reverse of x's. Sort and reverse are both polymorphic functions. So in the elaborated program, I need to be explicit that I'm calling reverse at type int, and that I'm calling sort at type int, and moreover, sort is overloaded. It's got this OR day constraint, so it takes an ORed int dictionary. I'm not going to dive too deep here, but it's an actual runtime value that is passed as an extra implicit argument to sort. So this is the elaborated program. This is the original source program, and it's part of the business of the type checker to cough up this guy, given this guy. So far, so good? Right, and the elaboration also has to do, we dealt with applications, the elaboration also has to do with abstractions, right? So here, if I've got foo, my foo here was not polymorphic. It was just list of int to list of int. Now here, this foo, same code, but now he's polymorphic for all a, or day, list of A to list of A. So what does he do? So foo has to start with he's got a for all type. He must start with a big lambda. And he's got an OR day constraint. He must have a lambda for some dictionary for OR day. And then he has his value argument, x is here, and it's explicitly typed with type A, or is it list of A? Oh dear, sorry, that should be list of A. And then we sort, so then the application bit as before.
Is it like the box concrete syntax?
Is it what?
Concrete syntax.
Is what concrete syntax?
The light blue box.
The light blue box is the elaborated program.
Right.
So you can imagine it as being written in a slightly larger language with explicit dictionary abstractions and dictionary abstractions, type applications, and dictionary applications. Just a bit of a larger source language.
You don't have that language.
We have some of that language. In Haskell, in fact, we have extended the language with explicit type applications like these guys, but not with explicit dictionary applications, because that might be incoherent. Yeah?
You made it sound like you decide to generate the big lambda and the d from the signature foo, but in fact, if you didn't have the signature, the type annotation,
yes, that's true. If the signature was not here, and we just gave this, we will infer this signature and cough up exactly the same elaboration. Thank you. Yes, carry on. Yeah. Okay? So, long story short, type inference takes a syntax tree and produces a new elaborated syntax tree, which is basically the same one with type decorations, including these abstractions and applications, and also every binder In the source program, which didn't have types on it, like this X is no type, in the elaborated program, the binders do have types on them. So does that make sense? So it's a very helpful thing for the type checker to do. And that means that the type checker has a type that looks more like expression, and then here's the expected type, and now it's a TC monad returning an expression. So simple enough idea, but very useful in practice, I think, which we found pursuing this consistently is good. Okay. So now enough preliminaries. I want to get to the main bit of this talk, which is about constraints, right, and generating typing constraints. So this is what I call the French approach to type inference, because I learnt it from Didier Rémy and François Pottier in their wonderful paper, The Essence of ML Type Inference, which is long and quite technical, but brilliantly written. It took me about 7 goes to understand this paper, but it was worth it, right? This is, if you're going to read one paper about it, it's just the basics. So go read it. So all I'm going to tell you is I'm just the sort of like the shill to interpret Pottier and Rémy for your benefit, if you don't already know. So their idea is this. You take the source program, and first thing you do is you walk over the syntax tree generating constraints. So when you finish that, you have an elaborated program. The generation process produces an elaborated program, and you have a whole bunch of constraints, as yet perhaps unsolved. Then you solve the constraints, and that generates a substitution that you're going to apply to this elaborated program. I'll show you a little bit about that happening to get you the final elaborated program. But also solving the constraints may lead you with some unsolved residual constraints that you can report as type errors. Right? This is the architecture of a type checker, and I want you to, that's different to this, in which all of, it's broken this arrow into several distinct chunks. Why is it helpful to break that big arrow into constraint generation and constraint solving? Why is that good? So here are 5 reasons why it's good. Number 1, constraint generation has a lot of cases, right? Haskell is an enormous language. So the number of syntactic constructs is, 50 or 100 or something, right? So there's lots of cases here, but constraint generation, pretty simple, right? So there's a lot of cases, each of which has pretty simple code. But the constraint solver is really tricky. Oh, man, if I had £1 for every hour I'd spent on the constraint solver, I'd be a rich person, right? So constraint solving is difficult, but constraints are written in a small language, which I'll show you very shortly. So it only has a small number of cases, but each of those cases is very subtle. Does that make sense? So what you don't want to do is to have a lot of cases, each of which is subtle, right? Many cases, easy code. Few cases, really tricky code. Much better way to factor your problem. Thank you, Didier. So another important thing is that the results are independent of the order in which the constraint generator traverses the program, right? In many type checkers, if you write a pair E1, E2, it'll type check. If you switch it round and it's E2, E1, no longer type checks, right? But there's some left to rightness in the type inference algorithm. There's no left to rightness here because the constraint generator just walks over the program, spitting out those constraints. The constraint solver kind of sees them all at once in some more, it has a more global view. It's much more it's much easier to make it order independent. It's not easy to make it completely, but it's much, much easier. I think this is a big win myself, but it's tiresome if your program changes. If minor syntactic changes to your program change radically its typing behavior. Apart from anything else, it's hard to specify, right? What's the spec of the type system? Okay, elaborated. Generating the elaborated program is relatively easy. The act of constraint solving is more or less filling in the holes of the thing, as I'll show you. And error messages are generated. Error messages are really hard to generate. Spreading the error message generation code all over the constraint generator is pretty hard. In fact, I'll show you. Here is a sort of breakdown of lines of code in GHC stuff, right? So constraint generator, 11,000 lines of code, and not quite as many lines of comments. Constraint solver, 6,000 lines of code, and rather more lines of comments than code, because it's tricky, right? Error message generation, 9,000, a monstrous amount of code is just to deal with trying to generate good error messages. Splitting that out into the bit that is right here, right, looking at a constraint and spitting out error messages is much easier than spreading it out all over here. So it is in practice, I found this to be a really big win. That's really what my sales pitch to you today is Chaps, this is the way to write type inference algorithms, and your life will be happier if you adopt this in a wholesale way. Okay, of course, Didier and François, they don't do this in OCaml. Is this the way it happens? Not at all. But we have adopted your... in the future. But we have wholeheartedly bought into your plan. Okay, so let me just say a little bit more about each of these steps. Right, so constraint generation. How do constraints get generated? What does it really look like? So I'm going to show you. Well, here's my type checker. Remember, we're familiar with this type signature, right? It's in some monad. And we're going to provide some primitive that lets us emit a constraint. We'll have to see what a constraint is, but emit is just going to stick it into the... What does it mean to stick it into the monad? Imagine that the monad is carrying a bucket of constraints, and we're just collecting them all, and then finally collect constraints, takes a computation that generates constraints, and gathers up all the constraints generated by this computation, and will return them as a paired up. So collect constraints of some computation thing, will run thing, gather the constraints, and return a pair of the constraints with the value returned by thing. But this guy here emits no constraints of its own, right? Because they're all the ones that came from inside here appear here. Does that make sense? So it's just a standard monadic approach towards sort of gathering constraints in a state. Good. So the monad here is a sort of writer monad here that just gathers constraints up. We don't need to read. It's just a writer monad. Okay? Simple enough. Monad was already there. We're already paid for. Whenever anybody says something is for free, what they mean is you've already paid for it. Right? And this is true here. Good. Okay. So what are these constraints? Well, there are not very many of them, actually. A constraint is either empty, or it's a pair of constraints, or it's a class constraint, like show A or ord B or something, or it's an equality constraint. We'll see those in a second. Or it's an implication constraint, which I will tell you about in about 5 minutes' time. But when I said the constraint language is small, this is what I meant, right? Because really, these first two are barely worth talking about. They're just like a collection of constraints. So really, there's only 3 forms. That's not very many, right? It's amazing how hard it is to deal with those 3, though. Right, so here's what the constraint generator might look like for an application. What do we do? Well, so it's not exactly like this, but it's kind of close. Let me see. This is binary application. So forget this morning and vector, right? I'm just taking the simplest case, a binary application. I'm going to infer the type of E1. Remember, infer is just a little wrapper around that TC function. Remember that from this morning? So I get the function type. Then I'm going to make, the function type ought to be an arrow, shouldn't it, right? But it might not be an arrow yet. So what I'm going to do is I'm going to make up fresh unification variables for the argument and result. And then I'm going to unify the function type with this arrow type, all right, because they should be equal. And then I can check that E2, the argument has this argument type thing. Now, this isn't exactly what happens in GHC because of the stuff to do with higher rank that I was describing, but it's I wanted to make something simple enough I could show it on one slide for constraint generation for application. But the thing I want to point you to here is this call to unify. Now, this doesn't mean actually unify the function type and the arrow. It means emit a constraint for that equality. That's all, right? But there is an opportunity that sometimes you can, on the fly, say, he's trying to unify list of A with list of B. Well, I could do that. I can do the list part easily, and I'll just emit the constraint A equals B. Right, so this guy can do a little bit of on-the-fly unification really quickly because it's a bit more efficient than emitting the constraint. But the idea is it's exactly as if you just emitted the equality constraint. Garrett?
But is it important that you didn't also unify A and B?
Is it important that I did? Well, where was A and B?
Well, you said list of A and list of B.
So
you can do the list part.
Oh, no, sorry. Is it important? So when I said you could quickly look ahead when you're trying to unify list of A and list of B, could I unify A and B? If A and B were, say, unification variables, alpha and beta, then you could unify them. But supposing there were scolums from something, but there was maybe an equality constraint in scope, which mumble. So yes, there are lots of times when you can do a quick fix, including actually performing unification. But if there's any doubt, if anything tricky happens, you just say, I'll emit the constraint anyway, and send it off to the constraint solver, who is very clever, right? You do the stupid things right away. The clever things you leave for that wonderful constraint solver. Okay? Yeah, Gabriel.
Performance difference does it make?
Say again?
You say this is for speed.
Yes, for speed. I don't actually know how much difference. It would be easy to find out, but I don't actually know. Probably not that much. but a bit. Okay, so that's how constraints get generated. Yes?
So there's also a missing piece here, right? Presumably you have to be tracking source information.
Oh, you're talking about how can I generate good error messages if I don't know source information? So when I say unify here, I emit an equality constraint, but I also attach to that constraint provenance information that says, where did the constraint arise? Where does that provenance information come from? It, of course, is in the monad, right? And so when I come across a node here, the first thing I'm actually going to do, right before that do, is to extend the monad with something, say, I'm in this application, or something like that. Yes, thank you. So every constraint does have its provenance with it as well. Yep, Joachim.
So, if I have a list of constraints and I don't have the microphone.
I'll give you my microphone. Go. Yeah.
So, suppose I have a list of constraints and they are just equality constraints, right? And I solve them by either they are equal, so I throw the constraint away, or they are not equal, so I substitute one for the other in the remaining constraints, and I risk quadratic runtime for solving the constraints.
Oh, I'm going to show you the constraint solver next. Funnily enough, that's the next thing.
All right.
So we'll talk about constraint solving. So now we've generated these constraints. So in principle, we've walked over the whole program and done no solving. Now we have the constraints and we're going to solve them, right? So how does that work? Well, here's a bunch of equality constraints. Joachim, right? A couple of, here's just two. So what do? So the idea is I repeatedly pick a constraint and try to solve it, and if I can, I make it simpler, and if not, I move on to the next one. So here, the first one I pick is list of equals list of gamma. Fine, I can solve that by decomposing, but I have a new constraint, beta equals gamma, to solve. How can I solve that? Oh, perhaps by unifying beta to b gamma by side effect. So then I solve that. Now I've dropped down. Now I've got this. Right, and now I've got to solve this one, so I decompose that, and then delta equals int, and I unify that, and that leaves me with ord delta, but now it's being unified to b int, so that's just ord int, and I can solve that. Did that answer your question? That's what the constraint solver.
Okay, so the question is sort of, in the talk this morning, you had this bidirectional type checking, whereby you sort of find the inconsistency immediately, whereas with this type checking algorithm, do I pay with a slower runtime complexity?
No, so the question is, how does this relate to bidirectional stuff? All the bidirectional stuff is here, interestingly, right? But bidirectional, all that up-down stuff we saw this morning, that occurs over here. By the time we generate constraints, bidirectional stuff completely dealt with. Bidirectional stuff deals with the quantifiers, right? And these constraints are mostly monotypes. Yeah. Okay, so let's see. So that's roughly how constraint solving kind of goes. You can see that. So all we're doing, this step at a time thing that I'm showing you here, that's just Robinson's unification algorithm, isn't it? Right? Nothing new there. It's just expressed as a kind of rewrite system. But there are some other things going on. There's these class constraints, and also, as we'll see shortly, we have some given constraints. So it gets complicated at the end. Right. Next step, how does solving affect the source program? Well, what I'm actually going to do, what actually happens is that the elaborated program is full of unification variables. You might say lambda x with type alpha, where alpha is a meta type variable, unification variable not yet filled in. When the constraint solver fills it in, which it did here, right? That, as it were, affects by side effect. Ooh, this is an imperative program. In the heart of GHC's type checker is an imperative program. But so we fill in all the holes in the elaborated program. That's how the two are connected. It's funny, this generates quite a big data structure that's completely separate as this data structure, but these constraints all have, as it were, pointers into the elaborated program. But it works very, very nicely and very simply and robustly. That was another idea from here. Okay. All right. Last thing I want to tell you about is, yes, we have 9 minutes. In fact, actually 10, maybe. Level numbers. Right. So also, I learned all about this from your paper about level numbers. Actually, I think it was a tech report. I don't know whether it's shown up in a paper. Maybe it has. It's another folklore thing. And you probably learned it from somebody else. You're probably going to deny inventing it, right? But I'm going to tell you anyway. Right, so, oh, beg your pardon, wrong direction. Now, what happens when I am type checking something like this? So here's just focus your attention on this lambda here. And this double colon is a Haskell source level type signature, for all a to a. So it's a claim that lambda y dot x has type for all a to a. Does it? Of course not, because it's got this free variable x, which is bound outside this for all, right? So something is wrong here. But look what happens if we sort of naively generate constraints. We might say, well, you know, the F2 must be a beta to gamma, so X will get type beta, and then in the body here, I'm going to get, dear, what am I going to get? I'm going to, have I got this completely wrong? I think maybe no, that's right. Then gamma, this result type here, that's kind of going to get connected up with X's type. So, but the A here comes from the signature. So am I allowed to unify the result type of the whole function, F2 lambda X dot something, that something, gamma, am I allowed to make that equal to, by sort of unification, with this for all A thing? Obviously not. That's wrong, right? It's just wrong. So what to do? I can't tell you for how long I sort of scurried around with sort of half-baked implementations, and then I learned from Paris, and now we just have level numbers. So what do? Is just say, well, look, when we walk inside this for all, we're going to, first of all, every type variable is going to have a level number attached to it. It's just permanently part of that, including both meta-type variables, these Greek things, unification variables, they have level numbers, but also scholars like the for all of a universally quantified type. So here then I'm going to, when I walk inside the for all, I'm going to say, inside a for all, I've got this thing A in scope, but it has level number 2, right, because I'm walked inside something. And then I've got gamma from level 1, that's from the outer thing, it's got to be equal to this A from level 2. And then we're going to have the rule that says I cannot unify a unification variable from an outer scope with a scolum from an inner scope. And so it's a pretty simple rule. You just look at the free variables of the type you're unifying with and decline to unify. And that leaves you with a residual constraint that you can then report. So it's sort of super simple, but it needs this implication constraint thing, right? What is this? This is one of those constraints. Do you remember? Have I repeated the syntax of constraints? Bother, I haven't. But the syntax of constraints, do you remember, included for all a W, double arrow W, and here it is here. And this, incidentally, is totally part of Didier and François's paper. Just took me a while to understand what they were doing. And these implication constraints, super good, right? So the idea is pretty simple in the end. The type checker monad carries around yet another thing, which is the ambient level of the type. Whenever you make a fresh meta-type variable, you just take the ambient level. And at something like a type signature, when you walk inside the type checker, we scholemize it, scholomizing to the, you bump the level, scolomize the type variables to the new level, and then check the, in this case, the expression inside with the body type, with the A, the bound variable substituted by this level numbered scolum, and away you go, right? And then you build the implication constraint. And the implication constraint is just emitted into the monad to be solved later. Right, so you get a big tree of constraints. I'm going to skip, am I going to skip promotion? I've got 2 minutes. I'm going to skip promotion, yes. So I just want to say this idea of level numbers and implication constraints scales nicely to handle lots of different things. And I just want to quickly enumerate the different things. Number 1, when you're inferring types, when you've got something without a type signature, this is Gabriel's point, right? We need to say, I want to quantify over all the type variables that are not free in the environment, right? What do you mean, free in the environment? That's just a level number question. Very easily solved, right? So no walking over the environment to find its free variables. Pattern matching with existentials and dictionaries. Here's a data type in Haskell. This is a type with no parameters, but inside this data constructor has this funny polymorphic type, result type T, of course, but it binds an existential variable A and a sort of dictionary, show A. That works very nice. I'm now going to have to go quickly. You end up again with implication constraints. That handles that very beautifully in the same way. There's a trickiness with GADTs right back in the original GADT paper. It says if I've got a function like this, what does this say? T1 is a function that takes an int and returns a T int. So when I pattern match on T1, I know that this A here is an int. Sorry, this is a different T than the previous slide. So if I say this function Tx arrow x, now this x is an int, but perhaps the function has type TA to A, because inside this right-hand side, A and int are the same. So there is no principal type for this f. So in the original paper, we talked about, oh, so for these kind of functions, we want to reject the program on the grounds there is no principal type. But then you have to say, by what mechanism are we going to reject it? And it turns out that this whole implication constraint infrastructure gives you just enough leverage to do that nicely. Elaboration, this is number 4, the things that it scales to handle nicely. When we got these funny data types that bind dictionaries, like this guy, right? Then we might have some constraints inside that we must solve using the constraints bound by the implication. So we're going to generate some runtime bindings. And so, in fact, this program elaborates to have a let binding. And this let binding here, is like a unification variable, really, in that it's just the name for a mutable reference. And right there in the implication constraint, we say, oh, this is a pointer into this part of the tree, and when we solve a constraint using this guy, we should add a binding to that. So it scales nicely to handle the solving dictionary constraints with involved values. Lastly, quantified constraints. This is a fairly recent, like only 5 years ago, innovation to GHC, where you've got functions which don't just say ord a double arrow blah or show a double arrow blah, but they have something on the left of the double arrow which itself is quantified. Hence a quantified constraint. I do not have time to pause here. I just want to say the very same mechanism makes this easy to handle. So, big picture. This is essentially what, let's see. Let me just stop here, right? So, I think this game of generate and solve, with the glory of implication constraints, is just sort of on all axes a better way to write type inference engines. And again, you should have a sort of reason not to do it. And I repeat my grateful thanks to Parisians for telling me about this. This is the way GHC's type checker is. And I think that more should be like this. It's great. Thank you.
We have time for 1 or 2 questions.
I'm curious about how you generate coercions for GADTs, because there may be many qualities in the context that justify why A would be equal to B or int, and then you have to generate a coercion term. What's the strategy there?
So you're quite right that you're talking about coercions, right? Because your point is that when GADTs are involved, the pattern match actually binds a coercion, and we're going to elaborate. When we have a unification constraint, like where was my syntax of constraints here? This guy G, the evidence for inequality is a coercion. So it works by exactly the same mechanism as type classes. We just generate coercion bindings in effect. And it doesn't really matter which equality you use to solve it, so long as there's one available that's in scope. So I don't think we've had trouble with saying which of the many possible ways to prove it. Any proof will do.
I have a possible reason not to do things like this, then I'd really like to be told it is
yes,
that works anyway.
Good.
But also it's not one that applies to GHC. So languages which aren't Haskell often do some amount of type-directed disambiguation of names, type-directed lookup of fields. And that means that by the time you're doing scope checking of like a record field access, you need to know some stuff about the types already. So compilers that I'm familiar with that do this do it because they don't work in this style. They solve some of the constraints as they're going and use those partial solutions to decide what next. Have you thought about doing that kind of type-directed stuff in this style?
So, in a way, the setup I've described also does something like that, in that when I said that this part, the constraint generator, deals with pushing types down, it really deals with all the placement of quantifiers, right? It knows where the for alls are. When I said it generates the elaborated programming, all the for alls are placed in the right place. So there's some amount of type pushing up and down that's happening here, right? But it's very statically defined what that is. It's not sort of, you solve all these random constraints. It's very programmatic. Now, it's possible that the type-based name disambiguation that you're describing, it's possible it could be expressed and specified here. If it required some complicated constraint solving to discover which of the many x's you meant, that would be a bit of a worry. But so then I agree that it would become a lot more complicated, right? But maybe you could do it over here. And there is precedent for that in that we're already doing that for quantifiers effectively. All the quick look stuff, for example, is right over here. Quick look entirely over here. All that stuff this morning, all over here. Yeah. Well, here, I should say. Yeah.
So record dot syntax essentially does it with constraints.
So, yeah, so another plan for multiple fields is to encode record accesses, using a sort of type class constraints, which is what Haskell's new sort of has field constraint is all about. And that does let you postpone it off to here, but by expressing the things you need to know in the language of constraints, in effect. But a more ad hoc, that's when it's not a more ad hoc sort of overloading, you might want to handle over here. Yeah. Gabriel? Yeah?
And I guess that is made easier by the lack of, it's made easier because you gave up on local generalization. Otherwise, you can have interaction between generalization inside the term and this
yes,
constraint.
as ever, very insightful question. So now, what happens if I have a local let, right? If I've got a local let and I want to generalize, I've got some constraints arising over the body that have not yet been simplified, not yet been solved, right? So I could just abstract over all of those constraints and get some kind of giant type, like for all A, 100 constraints, double arrow, blah. That would not be very cool, right? So what we do in GHC is either we say, don't generalize local lets at all. Good plan, by the way. Let should not be generalized. Little paper about that. But if we want to generalize, and many people do, I regret to say, then we just say, damn the torpedoes. We'll solve the constraints. We will call the constrolver solver during constraint generation and just do the best we can. So now you probably could cook up an order-dependent problem, right? Yes, I mean, I think so there you're kind of a little bit outside the envelope of what I think is truly principled. But hey, it just works fine in practice, I'm embarrassed to say. I almost wish it failed more brutally. Yeah, Didier.
So actually, in this case, you only need to solve a fresh part of a constraint. This is what we did in the essence of ML-type inference.
You mean the bit that's concerned with that function?
With using the levels. So you want to solve it up to the level to which you want to generalize. You don't need to solve the order constraints.
Yes, so if you've got constraints, when you're solving the constraints for a local let, if you've got constraints that involve only variables, bound at an outer level, you can just not solve them and leave them on one side. No need to solve them, yeah. It's just the ones that are local. And even the ones that are local, if you can't solve them, you can always abstract over them, right? Because after all, you'll expect... Then you're going to duplicate the solving, right? So it's kind of optimization thing. Yeah, that's exactly it.
All right, let's thank Simon again.
Yeah, good.